Hi, this is Dr. Pratima. Let us discuss the extrinsic semiconductors p-type. I am a faculty in Physics, Institute of Aeronautical Engineering, Hyderabad. This is an extension of my previous video lecture where we have seen the n-type semiconductors in the extrinsic semiconductors. We have seen there why they are called as n-type, what will be the band picture and the bond picture there, and what will happen as the temperature is raised, and what are the Fermi level changes as the temperature and the donor atoms are increasing in number. In this video lecture also, we will be seeing what are intrinsic semiconductors, once again we'll recall, and what are p-type semiconductors, how are they formed, and how can we arrive at the concentration in the p-type semiconductors, taking the majority charge carriers, what are they, and how the variation of the Fermi level will happen when there is a raise in the temperature as well as raise in the number of the acceptor impurities. So now this is again a recalling of the previous lecture. For those who are attending my lecture for the first time, this will be a helpful slide for them. This is a classification of the semiconductors into two types based on the composition and the presence of impurities, where we have only this part. So depending on the presence of impurities, intrinsic semiconductors is the first part, which is pure. These semiconductors are very poor in the electrical properties because they don't conduct, and in order to enhance their properties, we are going for the extrinsic semiconductors, where we try to alter the semiconductors by adding some either third group or fifth group elements. So when we added the fifth group elements, we have seen the n-type semiconductors to be forming, as the majority charge carriers were the electrons. But as of now, from this extrinsic semiconductors, let us see the p-type. So the conductivity of an electron is being enhanced with the third group or the fifth group, and this method is known as doping, and the impurity whichever you add may be a dopant, and these are the fifth group and these will be the third group elements for mostly studied intrinsic semiconductors, germanium and silicon, and even more are there in the periodic table. So the p-type semiconductor, the trivalent impurities are added. It may be either aluminium, gallium, indium, etc. to a pure semiconductor like germanium or silicon, which I have told you already. So it has only, whatever you are adding to the silicon, it has only 3 valence electrons. So if it has 3 valence electrons, then what will happen to the other state? Because silicon has 4 valence electrons, and in this 4 valence electrons, with the 3 added electrons through the dopant, which is aluminum or gallium or indium, they will be covalently bonded, but one is still being remained as a whole. So this being a vacant site, it can be offered, or the dopant can be offered an electron by the mother lattice, which is the silica or the germanium. Okay, so this can offer. When this is offering, this dopant whichever you are giving is ready to accept that electron. Hence you call the dopants as acceptors. Okay, so what will happen if that electron is being given or accepted? There is a hole being formed. Thus, holes will always be dominating in number. Holes are nothing but the vacant site left by the electrons, which is nothing but a site which is left by a negative charge, leaving behind a positive charge in the site. Hence, holes are positive charged, and because these are majority in number, P for positive, hence these semiconductors are known as p-type semiconductors. So now, as you look the aluminium taking as the dopant with the 3, 1, 2 and 3 valence electrons being added into the silica lattice, where these 3 are being covalently bonded with the 3 neighboring atoms. One is left as a vacant site and the covalent bond is incomplete, whereas here they are complete. So this incomplete covalent bond will help in the assistance of the increasing of the conductivity. How? I will tell you how. So this silica may, as you give rise to the temperature, this silica can offer its one valence electron to this aluminium atom, and this, if it moves here, this will be left again as a hole. So this is what I have explained you, and if you take this and dope it into the silica lattice, what will be the picture? So this is the two-dimensional picture where boron is taken here. So you can see here even a hole being formed as a vacant site. So if, and the sharing of the electrons with the neighboring lattice is also given here. And if you take the band picture here, now that the silica lattice is offering an electron, where from can it offer? It can offer only its valence electrons. And where are the valence electrons? The valence electrons are always there in the valence band. So this dopants, whichever you are adding, will form an energy level called as the acceptor levels, because they are accepting the electrons from the valence band. Hence, they will form a level near the valence band, accepting the valence electrons as the temperature raises. So this is the valence electrons. And as the Fermi level is the energy level which has a probability of occupancy of the electrons, hence this Fermi level for this particular extrinsic semiconductor will lie in between EA and EV. Okay, so now, and of course the intrinsic Fermi level will always be in the center. So moving on with this, let's now see what will happen if T is increasing greater than 0 Kelvin. So before we have seen, in our previous lecture, we have seen the phosphorus atoms forming a level beneath the conduction band very nearly, and as the temperature rises, how those atoms have formed a positive ions we have seen there. So the same phenomenon here, if you have followed that lecture, this will be very easy for you to understand. First, there are electrons. Let me take it here, okay, for your better understanding. There are electrons, and these are the boron or the aluminium atoms. Okay, this is an atom. Try to understand, this is an atom. Now, I am slowly raising the temperature. At the initial rise of the temperature, what will happen? The boron atom is very nearer with one vacant site, right? If you're recollecting, it has one vacant site. Vacant site in the sense a positive charge. So, and an electron here very nearer to the boron atom in the uppermost level of the valence band, which is nothing but the valence electron of the silica. So, silicon atom. So, this valence electron will be attracted towards or grabbed or accepted by the boron atom, which is the dopant. So now what is happening? It will also gain the octet configuration, and this is gaining stability. Hence, gaining the negative charge, gaining stability, hence you call it as a negative ion. Okay, so thus, taking this positive ion, it has gathered a negative ionic ionization, leaving behind a vacant site which is a hole. So next may come the turn for this. Okay, it will take forming a hole, and this will become ion. Okay, after this, and next it may go. So what are you seeing here? More the number of the holes being formed. So what will happen still more and more? Suppose all of these are over. Okay, 5 I have added and 5 are over. Okay, So this also have converted to B minus. Everything have converted. So what will happen now? As I am still increasing, now comes the turn for this electrons to go and sit in the conduction band, leaving holes again here. So even if the electrons in the valence band are rising and sitting in the conduction band, there is still a possibility, even though now you are having an electron, still there is a possibility for the holes always to be dominated in number in this intrinsic in semiconductor, which is doped. Okay, so because the holes are being large in number, it is known as a p-type semiconductor. So as the holes are being formed when the electrons are being excited, there is always a probability for the electron hole pair to be formed and the regeneration recombination event to happen. So this is same as the n-type semiconductor. The understanding is the same. So what will happen to the Fermi level? So now the Fermi level in the beginning is here, as the probability for the electrons to exist is here. So now what will happen to it as the temperature is being risen? Let's try to understand it. Before that, let me compare what are the differences between the intrinsic semiconductor and the two types of the extrinsic semiconductors. So what is happening first is there are positive charge, electrons here in the valence band, and the conduction band was empty at T is equal to 0 Kelvin. But now as T is increasing, what will happen is these electrons are exciting to the conduction band and sitting here as a negative charge, leaving behind a positive lattice, which is a hole. So this is known as an intrinsic semiconductor. This is what is happening in intrinsic semiconductor. But now what is happening here is you will have to understand as many as the number of electrons, so many as the number of holes. So there we end up there. But now here there is something which is different, because you are adding the impurity, which is in n-type, which is a pentavalent impurity. Pentavalent impurity in the sense you are taking there is one dangling free electron. So that will be forming a layer which is ED beneath the conduction band EC, and as the temperature is increased, this will donate its one valence electron to the conduction band and turning it to a positive ion. Okay, so now here what is happening? You are adding a trivalent impurity here. Trivalent impurity in the sense there is one vacancy. So the trivalent impurity, as you are raising the temperature, before raising the temperature, it will form a level very nearer to the valence band, because this accepts the valence electrons from the host lattice, which is the silica. Hence, it forms a level which is very nearer to the valence band. So now, as the temperature rises, this boron, if you take, it will accept this electron, making a positive charge. That is a hole being formed here. So this being turned as boron minus, that is an ion. So these three are the major differences between intrinsic n-type and p-type semiconductor. And because the holes are the dominating charge carriers and the transitions are happening here, EF will be lying between the acceptor level and the valence band. Whereas here, the Fermi level will be lying between the conduction band and the donor level. So these are the things which you have to really remember, because any one of these can be asked for you in your assessment exams. So moving ahead, if we try to calculate the carrier concentration, where we will later see how the Fermi level will be increasing, again, like how we have seen in my previous video lectures, taking Na as the acceptor concentration, which is nothing but the number of acceptor atoms per unit volume of the materials, which is forming which is also having an acceptor energy level, having energy Ea. If you take it as Ea, the number of ionized acceptors. For an acceptor to get ionized, there should be first acceptor atoms. So the acceptor atoms you need to have per unit volume, that is Na. And for these levels, the probability for the ionization to take place also should be there. The probability for the ionization in the sense what? The probability for the electrons in the valence band to be accepted by the dopants also. That probability also should be taken, which is given by the Fermi-Dirac distribution. So taking the first, you need to know how many holes are there in the valence band. Why? Because as many the number of holes in the valence band, so many the number of ionized acceptors will be there. So for those who are seeing my lecture for the first time, I'll try to explain. These are the valence band, and the acceptor atoms are being sitting here. So let me name it as Ea, and this is Ev. So if I am trying to raise the temperature, the valence band will be having electrons. So what will happen? The valence electrons will be attracted or received by the Ea, and which is boron. Then it will turn up as negative ion. So this will be having a hole. Okay, so now one boron ion, one hole. So now, as you are still raising, the second electron will be accepted by the second boron ion, boron atom turning as boron ion, and you have the second hole. So two holes, two boron ions. So thus, even at a very low temperature, the number of holes in the valence band should be equal to the number of the ionized acceptors. Why I am saying even at very low temperature? Because the gap is very less. So even a small temperature is enough for this excitation to happen and go and sit in the site of which is vacant in the dopant. Okay, so now you have the number of ionized acceptors, you have the density of holes, equate both of them and solve for EF. So before solving for EF, you have exponentials, bring out the exponentials to one part and the rest to the another part, and e to the power of m by e to the power of n is equal to e to the power of m minus n. And if you have to get rid of e, you have to take the logarithm on both sides, take the logarithm on both sides and solve for the logarithm. Let the logarithm be like that, take this kbt to the other side, and if you can apply for this t is equal to 0, then you can see clearly that mathematically we have proven that EF lies between EV and EA. Okay, so and at t greater than 0 Kelvin, what will it happen? Slowly, as the temperature decreases, it will slowly drop down towards the valence band, and as you still more increase, what will happen? See, so what will happen here? The Fermi level, this is the acceptor energy level, and this is the conduction band. The conduction band is very higher, which we are not taking much into consideration. Now we have the valence band, and this is the intrinsic Fermi level. Intrinsic Fermi level means for whatever the Fermi level should be there for an intrinsic semiconductor. But now that the ions are forming at the acceptor level, because of the transitions which are happening between the valence band and the acceptor level, the Fermi level will be here at t is equal to 0 Kelvin. Okay, now as the temperature raises, what will happen? The ionization will happen. So as the ionization is happening, there is a transition of the electrons to the higher side. So it will be traveling up, and after the whole ionization is taking place, what will happen? These electrons, whichever the first electron, it may be received here, the next electron, it may be received or accepted by the next, becoming boron minus acceptor ion. After the ionization is completed, as we had very little impurities, so what will happen, the next term is for the, sorry, I'm so sorry here, this is Fermi level. So if I take this as the valence band, let me take EV here and EVB as the bottom. So first, these valence electrons will be received by the borons and becoming boron ions, and these electrons are received, leaving a hole. So now still if you increase, what will happen, the next term will be for the next electron to raise into the conduction band, leaving a hole. Next is this, okay, leaving a hole. So thus the Fermi level will start shifting, okay, and once, if you still more increase, what will happen, now this electron is forming here and hole here, there is a probability for the electron hole pair to form, and recombination also can happen because the bond, the covalent bond is being ruptured here. So what will happen now, the Fermi level will slowly increase as you're raising the temperature and reach the intrinsic Fermi level place. But if you take the same phenomenon, taking large number of the dopants, that means as you see here 10 to the power of 24, what will happen is, as there are more number of boron atoms, the time, it will need more time, that means more the temperature. You will have to give the temperature still more the number of the dopants, you will have to give more temperature. It will take some more time. As you are heating, it will take some more time for all the boron atoms to be ionized. So though it had the peak, the curve has raised here itself, okay, now it will raise here slowly. It started and then it raised here, and even at this particular temperature it has reached, but as the density of the acceptor atoms have been increased, even at 500 it didn't reach the intrinsic Fermi level. So this is how the Fermi level will change with temperatures and the acceptor atoms. So hope you have understood all these things. Let's take this into consideration and go for the density of the holes. Now that you have the number of the holes in the valence band, you can go for the EF, which you have already derived, and substitute it here. Okay, if you substitute it here, further simplifying, taking this minus inside and just substitute and simplifying it, you can arrive at this particular expression just as you have done previously. Okay, so now if you have really followed the lecture, here are the conclusions. So extrinsic semiconductor is any doped intrinsic semiconductor. The dopants, whichever you are adding, may be trivalent or pentavalent. Trivalent is nothing but P-type semiconductor, and if you add pentavalent elements, it will end up as N-type semiconductor, because in P-type semiconductor a vacant site will be left because you are adding trivalent impurities. They will have only 3 electrons which are covalently bonded with 3 valence electrons of silica, which is the intrinsic semiconductor, whereas one other valence electron of the intrinsic semiconductor is left vacant, which will act as an entity to receive any heat you give and moves to the leftover site, leaving again a hole. Thus holes are the majority charge carriers, which are positive charge, hence you call this semiconductor as P-type semiconductor. And because this dopant, whichever you are giving, is accepting the electron which is given by the host lattice, you call it as an acceptor, and this will form a level which is EA near to the valence band. And the majority charge carriers, as I told, are holes, and at 0 Kelvin the Fermi level will be between EA and EV, and as you raise the temperatures, the acceptors gets ionized and the breaking of the covalent bonds may lead to the electron hole pairs. And as you still raise the temperature, what will happen to the EF is it moves towards the intrinsic Fermi levels, but when you compare it with higher donor concentration, the movement will be very slow when compared with the lower level of concentration, because it takes time for the higher number to get ionized. Hope you have followed all these things. Wishing you all the best. I'll see you in my next video lecture. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.